Welcome back to the deep dive. Today we're taking a deep dive into something really foundational if you're trying to get your head around how huge amounts of information get managed in, well, in our on-demand world. We're going to unpack the backbone of high-performance data storage, fiber channel architecture.
That's right. Yeah, if you've ever sort of wondered how the digital infrastructure that powers pretty much everything, cloud services,
Okay.
streaming media, how it handles the sheer volume and speed of information, then this deep dive is definitely for you. We're basically going to pull back the curtain on fiber channel or FC storage area networks, SANs,
Right.
looking at everything from their basic building blocks, how they talk to each other, all the way up to the advanced designs that make them so incredibly robust.
Okay, so our mission today is pretty clear.
Mm-hmm.
Give you a structured understanding of FC architecture. We'll trace its evolution a bit, demystify those protocol layers.
Which can seem pretty intricate at first.
Exactly. And even explore how it all plugs into modern virtualization.
Right.
You should walk away with a much clearer picture of what makes this tech so critical for high-speed, reliable data access. Okay, let's jump in. So maybe let's set the scene first. Picture, I don't know, a rapidly growing business, maybe early 2000s. They're just drowning in data.
Yeah, that's a good time frame.
And their traditional storage systems are hitting a wall. They're struggling with the volume, the speed, everything needing to be constantly accessible. Like trying to drain an ocean with a teacup, basically. What problems were fiber channel SANs really designed to solve back then?
That's a perfect analogy. I mean, the explosive growth of information just demanded a completely new approach. Organizations needed to store, protect, manage data efficiently, often needing, 24/7 availability.
Nonstop.
Yeah, exactly. Traditional stuff like direct attached storage or basic network file sharing, it just couldn't keep up with that scale or the need for just-in-time information. So FC SANs and ITNs, too, they stepped in as these high-speed network-based storage solutions. Fiber channel itself, it's a technology specifically engineered, really, to provide incredibly fast data transfer between servers and these large-scale storage systems. And it's kind of unique because it can run over both optical fiber for long distances and serial copper cables for shorter runs.
You just mentioned fiber channel, FIBRE, for the protocol, and then fiber optic, FIBER, for the actual glass cable. Does that distinction ever trip people up in the real world, or is it generally pretty clear?
Oh, it definitely can be a point of confusion for newcomers, yeah. But generally in the industry, it's pretty well understood. Fiber channel is the protocol, the set of rules for communication.
The language.
Exactly, the language. While fiber optic is the physical medium, the glass strands carrying light signals, like you said, the language versus the phone line. And as for the building blocks, well, an FCA-SEN, fundamentally, it's a dedicated network. It connects servers and shared storage devices. We often call these nodes.
Okay, nodes.
Yeah. And the infrastructure itself.
Yeah.
It's made up of node ports. That's the physical interface, the specialized cables, connectors, and then interconnecting devices like FC switches or sometimes older hubs, all managed by SAN software. Every node, whether it's a server, storage array, tape library, whatever, it needs one or more ports. And these ports operate in a full duplex mode, meaning they can send and receive data at the same time, like a two-way highway, basically.
Got it. That two-way highway makes sense. So when we talk about how these nodes actually connect, how they form this network, what are the main ways they interconnect in an FCSN?
Well, while there were older ways, like loops, the most dominant and definitely the most scalable option today is the fiber channel switched fabric, or FCSW network.
Fabrics.
Yeah. Unlike those older loop setups where devices basically shared a single path, kind of like a party line.
Right. Everyone hears everything or waits their turn.
Exactly. A switch fabric provides dedicated point-to-point connections. Think of it more like a massive telephone exchange. Each call gets its own line.
Makes sense.
And the real advantage there is scalability and resilience. Adding or removing a device is minimally disruptive. It generally won't affect ongoing data traffic between other parts of the network.
That flexibility sounds absolutely essential for large dynamic environments. Okay, so within this switched fabric, you mentioned ports earlier. What are the different types of ports devices use? Do they all do the same thing? Or?
No, definitely not. They each have a very specific role, kind of like different types of gates or doors at a secure facility. First up, you've got the N port, or node port.
N for node.
Exactly. This is an endpoint in the fabric. You'll typically find it on a host bus adapter in HBA.
That's the storage network card in a server, right?
Precisely. Or on a front-end port on a storage array. And it's designed to connect directly to a switch.
Okay.
Then there's the E port, E for expansion. This one's crucial for, well, expanding your network. E ports form the links between two FC switches. These create what we call interswitch links, or ISLs.
So we link switches together, the fabric's highways.
You got it. They're the superhighways of the fabric. Then there's the F port, F for fabric. This port is actually on the switch itself.
Ah.
And it's specifically designed to connect to an N port from an end device, like a server or storage. So it's the gateway into the fabric for those end devices.
N port talks to F port. Got it.
Right. And finally, there's the G port, G for generic. This is a smarter type of port on a switch. It's intelligent enough to automatically figure out its role when it starts up.
Oh, interesting.
Yeah, so it can operate as either an E port connecting to another switch or an F port connecting to a device, depending on what you plug into it. Kind of like a smart universal adapter.
Okay, that makes sense. So we've laid out the physical highways, the different kinds of on-ramps and intersections, but how do the vehicles, our data, actually know where they're going? And, how do they ensure they don't crash or get corrupted? It sounds like where the fiber channel protocol stack and its addressing system really come into play.
Exactly. Yeah, this is where it gets really interesting. At its heart, Fiber Channel Protocol, FCP, is essentially the implementation of SCSI commands, but over an FC network.
SCSI.
Yeah.
That's language storage devices speak, right?
Pretty much, yeah. It's a standard for connecting and transferring data with peripherals, especially storage. So FCP basically lets external remote storage devices on the SAN appear to the host operating system as if they're local devices. Plug right in.
Ah, okay. That's clever.
Yeah. And a key advantage of FC is its ability to sustain really high transmission bandwidth over pretty long distances. Plus, its sheer capacity for addressable devices is huge. Theoretically, we're talking over 15 million devices on a single network.
Wow, 15 million addresses. That's an incredible number.
Yeah.
But how does that actually work in practice? How does it translate into naming and finding things? Is it like an IP address on a normal network, or?
It's similar in concept, but definitely has its own unique flavor. In the FC world, devices get assigned a 64-bit unique identifier. It's called the worldwide name, or WWN.
WWN.
Okay. Now, unlike a dynamically assigned FC address, which we'll get to, a WWN is static. It's persistent, kind of like a MAC address on your Ethernet card. It's usually burned into the hardware or sometimes assigned via software.
It's permanent.
Generally, yes. And there are two main types. A worldwide node name, or WWNN, for the device itself, like the server or storage array.
Right.
And then a worldwide port name, or WWPN, for each individual port on that device. These WWNs are absolutely crucial for identifying devices across the SAN, especially when you're setting things up like zoning.
Okay, so WWN is the permanent ID. What about the dynamic address you mentioned?
Right, so the FEWN also uses dynamically assigned FC addresses. These are more temporary, more like an IP address assigned by DHCP. They're typically 24 bits. And there's a special service within the fabric called the name server.
Okay.
And its job is basically to keep track of the association between those permanent WWNs and the dynamic FC addresses currently being used.
Got it. WWN, permanent nameplate. FC address equals temporary seat number. Makes sense. So how is the actual data organized when it's flying across this network?
Good question. Data is organized into structures called sequences. You can think of a sequence as a single complete thought or command being sent from one port to another. It corresponds to one unit of information from the higher level protocol, like a single SCSI command and its response.
Okay, a sequence is a complete message.
Pretty much. And the fundamental unit within that sequence, the individual packet of data, is the frame. Each FC frame is meticulously packed, like a specialized shipping container.
Oh.
It has a clear start of frame marker and an end of frame marker, so you know where it begins and ends. There's a header, about 24 bytes, containing all the addressing info, control signals.
Where it's going, who it's from.
Exactly. Then there's the data field. That's the actual payload. It can be up to 2,112 bytes and often carries the SCSI data or commands. And finally, right at the end, there's a cyclic redundancy check, a CRC.
For error checking.
Precisely. That CRC is vital. It mathematically verifies the frame hasn't been corrupted during transmission. It guarantees data integrity. That precision is really why FC is so reliable for critical data.
Okay, that makes sense. So we've got the devices, the ports, the addresses, the data structure. But how do devices actually, you know, get introduced to the fabric and start communicating? What are the essential background services that make all this work together?
Right, so every fiber channel switch, it doesn't matter who made it, provides a common set of predefined fabric services. You can think of these as the essential city services that keep the whole fabric running smoothly.
Like utilities.
Kind of, yeah. There's the fabric login server. This is like the front desk or registration office for a node's initial connection process. It handles the first handshake. It lives at a specific, well-known address, FFFFE.
Okay, front desk.
Then there's the name server at address FFFFC. This is basically the Fabric's directory service. It's responsible for registering and managing all the node ports, keeping track of their WWNs, and assigned FC addresses. All the switches in the Fabric synchronize their name server information, so everyone has an up-to-date directory.
So everyone knows who's who and where they live.
Exactly. Each switch also has a Fabric controller at FFFFFD. Its job is to manage and distribute something called Registered State Change Notifications, or RSCNs.
RSCNs.
Yeah, basically alerts about significant changes happening in the Fabric, like a device logging in or out. The Fabric controller tells the relevant nodes about these changes. And finally, there's the management server at FFFFFA. This is the interface for your SAN management software. It allows administrators to pull information, monitor health, and, administer the Fabric.
Okay, so these services are always there at known addresses, providing these core functions.
Correct. They're fundamental.
So we've covered those essential background services. But before any device can actually send or receive application data, it needs to formally join the club, right? How does a server or storage array actually log in and become an active participant on this high-speed network?
Right. It's not just plug and play for application data. There's a specific multi-step handshake process involving 3 distinct login types. It ensures everything's set up correctly before real communication starts.
Okay, what are they?
First, there's the Fabric login, usually abbreviated as FLOGI.
FLOGI.
Yep. This happens between an N port, remember, that's on the device, like a server's HBA, and an F port on a switch. The node essentially sends a Fabric login server address we mentioned.
The front desk.
Exactly. This frame contains its unique worldwide node name, WWNN, and worldwide port name, WWPN. The switch receives this, says, okay, welcome, accepts the login, and assigns a dynamic FC address to that node port. Immediately after the FLOGI is accepted, the N port then registers its details, its WWN, assigned FC address, capabilities, with the local name server on the switch.
Okay, so FlowGA gets you in the door and gets you an address. What's next?
Second is the port login, or PLOGI, PLOGI. Now, once a device has logged into the Fabric via FLOGI, 2 specific endports need to establish a session directly with each other before they can exchange application data.
Ah, so this is peer-to-peer.
Precisely. They perform a PLOGI. During this, they exchange specific service parameters relevant only to that direct connection between them, like negotiating the specific rules of engagement just for their conversation.
Okay, makes sense. Fabric login first, then port login between peers. Is there a third?
Yes, the third is the process login, or PRLI. PRLI. This also happens between 2 endports after PLOG, but PRI relates specifically to the higher level protocols, the upper layer protocols, or ULPs, that are running over fiber channel.
Like SCSI, which you mentioned earlier.
Exactly. If SCSI is the ULP being used, which it very often is for storage, the endports use PRLI to exchange SCSI-specific service parameters. This ensures they can properly interpret each other's storage commands and data related to SCSI functions. So it's very precise sequence. FLOGI to join the Fabric, PLOGI to establish a peer session, and PRLI to agree on the application-level protocol rules.
Wow, okay. FlowShy, PLG, PRLI. A multi-step handshake for sure. So we've got the individual devices, how they talk, how they log in. Let's zoom out now. Let's talk about the architecture of the whole SAN. How are these fiber channel networks actually designed for scale, for resilience? And importantly, what strategies are used to segment them and keep them secure?
Right. Designing the overall SAN topology is critical. You typically choose from a few key approaches depending on the size and needs of the environment. One option is using mesh topologies. Now, these come in a couple of flavors. There's a full mesh where every single switch is directly connected to every other switch.
Everything connected, everything.
Yeah. Which sounds great for redundancy, and it is in very small environments, maybe up to, say, 4 switches. It minimizes the number of hops data has to take between any 2 devices connected to different switches.
There's always a but.
The but is scalability. As you add more switches, a full mesh starts consuming a huge number of ports just for those inner switch links, the ePort connections. You run out of ports for your actual servers and storage pretty quickly. And cabling can become, well, complex.
Yeah, can imagine.
Then there's a partial mesh. It's more scalable than a full mesh because you're not connecting every switch to every other switch. But the downside is that data might have to take multiple hops across several ISLs to get from a host to storage. This can add latency, and you have to be careful about managing traffic to avoid overloading specific links. It requires more careful planning. I remember in the early days, before Core Edge really became the standard, trying to troubleshoot performance issues in a large partial mesh. It was sometimes like trying to untangle a giant bowl of spaghetti just to figure out the actual data path.
Been there, maybe not with fiber channel, but yeah. So what's the more common approach now for larger setups?
For larger environments, the vastly more common and frankly more scalable choice is the Core Edge fabric topology.
Core Edge,
Yeah, this typically uses two tiers of switches. You have the Edge tier, which often uses less expensive switches. Their main job is connecting the end devices, the hosts, the servers.
Right.
Each of these Edge switches then connects upwards, usually with multiple links for redundancy, to a Core tier. The Core tier is usually made up of bigger, more powerful, high-availability switches, often called directors.
The big iron.
Exactly. And critically, all the storage devices typically connect directly to this Core tier. What this means is that most host-to-storage traffic only needs to cross one ISL, the link between the Edge switch the host is on and the Core switch the storage is on. This minimizes latency.
Ah, that's clever. Keeps the main traffic path short.
Precisely. And high-performance hosts, ones that need really low latency, can even be connected directly to the Core tier as well. This design gives you great connectivity, it conserves the number of ports you need overall compared to a large mesh, and it's much, much easier to expand predictably. You just add more Edge switches and connect them to the Core.
It sounds like designing one of these Core Edge SANs is almost an art form then, balancing the speed, the resilience, the cost, and planning for future growth. It's not just a technical checklist.
Oh, absolutely. There's definitely an architectural skill to doing it right, especially in complex environments.
And within these topologies, whether mesh or Core Edge, to manage the traffic flow, and crucially for security, we use something called zoning, right? How does that work?
Exactly. Zoning is a fundamental function provided by the fiber channel switches. It essentially lets you logically segment the node ports in your fabric into groups. And the key rule is, communication is only allowed between members that are within the same group, the same zone.
So it's like creating private networks within the larger fabric.
That's a great way to think about it. Private virtual networks, yeah. It's a critical security feature, obviously, because it prevents unauthorized servers from accessing storage they shouldn't. But it also has a major management benefit.
Oh, what that?
It dramatically limits the propagation of those registered state change notifications, the RSCNs we talked about earlier.
Ah, the fabric change alerts.
Right. Without zoning, if any change happens anywhere in the fabric, a port logs in, logs out, anything an RSCN message gets broadcast to every single node in the entire fabric. In a large SAN, that can create a lot of background noise, even network storms in some cases.
Like shouting fire in a crowded theater when it's just a small issue in one corner.
Exactly. With zoning, RSCNs are generally only sent to the nodes that are members of the specific zone where the change occurred. This drastically reduces that fabric-wide chatter and overhead, which is crucial in large environments.
That's a huge operational benefit.
Massive. And it provides that access control layer we mentioned. The zoning process itself defines a kind of hierarchy. You have zone members, which are usually the individual WWPNs of the ports.
Okay.
Those members are grouped into zones. And then you group one or more zones into a zone set. Only one zone set can be active in the fabric at any given time. And a single port, a single WWPN, can actually be a member of multiple zones within that active zone set, which gives you a lot of flexibility in how you define access.
So one server could be in a zone with storage array A, and also in a different zone with storage array B, but maybe server C can only see array B.
Precisely. It allows for very granular control. And zoning is often used in combination with another technique called LUN masking, which happens on the storage array itself.
Right, controlling which specific volumes a server sees.
Exactly. Zoning controls which devices can talk to each other at the fabric level, and LUN masking controls which specific storage units a permitted server can actually access on an array. Together, they provide pretty comprehensive access control.
So it's not just about who can talk to whom, but also managing that network chatter effectively. Are there any common pitfalls or challenges administrators run into when they're implementing zoning, especially in big dynamic SANs?
Oh, definitely. I mean, the main challenge is just managing the complexity, especially when things are changing all the time. New servers, new storage, decommissioning old stuff.
Hmm.
An incorrectly configured zone, maybe a typo in a WWPN, or forgetting to add a new host's ports to the right zone, that can easily lead to devices not being able to see their storage, which means application outages.
Yeah, that sounds bad.
It is. And when you have hundreds, maybe thousands of devices, just ensuring that every new device is added to all the correct zones and removed properly later without creating overlaps or leaving security holes, it really requires careful planning, good documentation, and often robust automation tools. Zoning is incredibly powerful, but it absolutely demands precision.
Precision is key. Okay, now let's bring this into the really modern context. We've got this incredibly robust, reliable fiber channel infrastructure. How do we make it even more flexible, more agile, more efficient? I'm guessing this is where virtualization really steps up.
Absolutely. Virtualization plays a huge role in optimizing modern SAN environments. One key type is block-level storage virtualization.
Block-level virtualization.
Okay. What this does essentially is it aggregates physical block storage devices, those LUNs, logical unit numbers we mentioned.
Potentially different storage arrays.
Exactly. From potentially different, maybe even older, heterogeneous storage arrays. It pulls them all together into one big unified storage pool. It creates an abstraction layer. From this unified pool, you then carve out and provision virtual storage volumes and present those to the hosts. The hosts just see these virtual volumes. They have no idea and, frankly, don't need to care about the complex mapping happening underneath.
Where the data actually lives.
Right. The virtualization layer handles all that mapping to the underlying physical LUNs on potentially multiple different arrays.
What are the big benefits there? Sounds like simplifying management.
Huge benefits. Management simplification is definitely one, but also things like being able to extend storage volumes online without disruption. Even if the underlying physical LUNs are full, you can just add more physical capacity to the pool. You can consolidate diverse storage arrays behind a single interface. And maybe one of the biggest ones is enabling truly non-disruptive data migration.
Moving data between arrays without downtime.
Exactly. The virtualization layer can handle moving the data in the background from an old array to a new one, for instance, while keeping the virtual LUN online and fully accessible to the hosts the entire time. It can even enable federation of block storage resources across multiple data centers. It's all about abstracting away that underlying hardware complexity and providing agility.
Okay, so block-level virtualization makes the storage itself more flexible. What about virtual SANs then, vSANs? How do they fit into this picture? Are they the same thing?
Similar concept, but applied differently. Virtual SANs, or vSANs, take that idea of logical separation and apply it to the fiber channel fabric itself. They enable you to create multiple logical SANs over a single, shared physical SAN infrastructure.
So partitioning the fabric itself,
Yeah.
like VLANs on an Ethernet network.
That's an excellent analogy. Yes, vSANs are very much like VLANs for fiber channel. You're taking one physical fabric and carving it up into multiple isolated logical fabrics. This significantly improves SAN security because you can completely isolate, say, your HR department's storage traffic within its own vSAN, separate from engineering's vSAN, even though they're using the same physical switches. Traffic cannot cross vSAN boundaries.
Okay, strong isolation.
Very strong. It also boosts scalability, interestingly, because the same fiber channel address can actually be reused in different vSANs without any conflict. And from an availability standpoint, if there's some kind of major disruption or fabric event, maybe a bad device spamming the network, if it happens within one vSAN, it's generally contained within that vSAN. It doesn't propagate and affect the other logical SANs running on the same hardware.
Containment. That sounds valuable.
Extremely valuable. And finally, manageability. Configuring vSANs is often far easier and quicker than building, cabling, and managing completely separate physical FC SANs for different departments or security levels. Administrators can regroup nodes, move a server from one vSAN to another just by changing software configurations. No physical recabling needed. So vSANs really minimize the impact of fabric-wide events, provide strong authorization control within a consolidated physical fabric, and simplify management.
It really sounds like layering these virtualization technologies on top of the core FC architecture adds tremendous power and flexibility.
It really does. It allows you to leverage the inherent reliability and performance of fiber channel while adding the agility that modern IT demands.
So we've really covered a lot of ground here. We've gone from the core reasons fiber channel SANs even came into existence, dealing with that data explosion,
Right.
through the intricate dance of ports like N ports, E ports, F ports, the login processes like FlowGI, PLGI, PRLI,
Handshakes.
the handshakes,
Yeah.
the architectural choices, mesh versus the much more common core edge designs, and how zoning provides that crucial segmentation and security.
And managing those RSENs.
Right. And finally, how virtualization, both block level and vSANs, adds these layers of abstraction, flexibility, and control on top. It's a complex but incredibly high-performance world, isn't it? All designed fundamentally to make sure your data is where it needs to be exactly when you need it.
Absolutely. Understanding these components, how they fit together, how they interact, it's really crucial for anyone looking at the foundational layers of enterprise IT infrastructure today. Fiber channel isn't just about raw speed, although it has plenty of that. It's really about the combination of speed with reliability, the built-in scalability, and that precise level of control required for the most mission-critical applications.
Yeah, that combination seems key. Looking at all this, what really stands out to you about the sheer complexity and maybe even elegance required to move information so incredibly rapidly while ensuring both speed and integrity, all on such a massive scale? And maybe looking forward, how do you think this foundational technology, fiber channel, will continue to adapt, especially with even greater demands coming from things like real-time AI processing, massive IoT deployments, all needing instant access to vast amounts of data? How does this bedrock adapt?
Well, that's definitely something to ponder. And that's all the time we have for this deep dive. We'll catch you next time.